All right. Okay. So last week we considered a problem of constructing a graph that matches a given degree sequence. Okay, and then we try to find a kinetic graph to achieve the job. So today we're going to consider a similar problem, in the sense that we're going to construct a graph. Okay, and this time we want to have a graph that has as many edges as possible. Okay, so we want to have a graph that has many edges. But of course, we want to have certain properties. Okay, otherwise we can just build a complete graph. So the graph that we're going to construct today is called triangle-free graph. Okay, so what is a triangle-free graph? So first of all, a triangle is just three vertices connected by three edges. So this is a triangle. So a triangle-free graph is just a graph where you cannot find any triangle, right? So for example, this will be a triangle-free graph because you cannot find a triangle here, all right? So this is triangle-free. Okay, so let me give you an example that is not triangle-free, right? Okay, so for this one, it contains a triangle. Triangle is this one. So actually, there are multiple triangles in this graph. Okay, so anyway, as long as you have one triangle as your subgraph, this graph will no longer be triangle-free. So this is not a triangle-free graph. Okay. So today, our first goal is to construct a triangle-free graph that has the most number of edges. Okay. So we're going to fix the number of vertices, say 10. Okay. Okay. So you need to have exactly 10 vertices. And in your graph, you cannot create a triangle. Okay. And your mission is to add as many edges as possible. Okay. Okay. All right, so this is just a toy example where the number of vertices is just 10. So later we're going to generalize this idea. So say you have n vertices, and you want to create a triangle-free graph that has the most number of edges, and how to do so. Okay, and do you have a formula, for example, for the number of edges in this kind of triangle-free graphs? All right, so do you have any idea to construct such a graph? So 10 vertices, right? So, and you need to add some edges. Okay.所以这边要做的事情就是你要设计一个 graph 有10个点 ，OK， 然后这10个点你要尽可能加 edge 进去，然后你要做的事情是你不能让这个 graph 有 triangle 跑出来 ，OK， 所以你不能无止境的加 edge 进去，因为你一直加 edge， 迟早有一天就会有 triangle 跑出来。我们要问的问题是，你要怎么画这个 graph， 才可以让它有最多的 edge， 但一样不会有 triangle。Or if you think 10 is perhaps a little too large, then you can try like 6, okay? Or even 4, okay? So in fact, not necessarily even numbers. You can also try odd numbers like 5 or 7, okay? But I think it's easier to consider even numbers. Okay. So perhaps you can try 6, right? So you have 6 vertices, okay? So how to add edges without creating any triangle? So raise hand if you have a triangle-free graph that has 6 vertices, okay? And we'll see who has the most number of edges, okay? 所以你如果画一个 triangle-free 的 graph， 你就讲一下你现在有几个 edge。好，我们看一下最后谁的 edge 比较多。So if it's a complete graph, then it will have 15 edges. Okay, so certainly 15 would be too large. Okay, because once you have a complete graph, you have some triangle. Okay, so the number of edges cannot be 15. Okay. Any idea? Yeah. No. Oh, okay. Okay, so let's count. So I guess there are 9 edges, right? Yeah, so 6 on the cycle, and for like this diameter, you have 3 diameters. So 9 edges in total. Okay. So if you generalize this idea to like 10, let's try 8. No. Okay, like this one. Or you can do like counterclockwise and clockwise, right? So. Uh-huh. All right, so I think you can just like scan this cycle, and for every vertex, you consider like the 3 hop neighbors, okay? And you add an edge between this vertex and its 3 hop neighbors, right? But how to prove that this graph is triangle-free? This is not very clear, right? Okay, so I guess that's one problem. And another problem is to show that this is indeed the best you can do. Right, so for this one, for every vertex, you have two additional neighbors. The first one is like the clockwise neighbor, and the other is the counterclockwise neighbor. So for every one you have, but perhaps we're going to like double count some edges. So I think we should divide it by 2. Right, for this one, it has this neighbor and this neighbor. But when we consider this vertex, we also add this edge. So for every this like diameters, we actually count it twice. Mm-hmm.
考虑到1、2、3、4第4个点的时候，就到左下角了嘛。这时候它就不会往上建了，因为已经有一条线，所以它这时候会考虑的是，就它会根据这个左下角这个点，会根据你前面3个已经建完的那些 edges，然后来判断还有没有可以新增 edges。
Yeah, no, but I just want to have a formula for the number of edges. Yeah, so at least from this example, we can have 8 plus. So we have 16 edges. Okay, so for this graph, can you add more edges to the graph without creating a triangle? When n is 8, the number of edges in the complete graph will be 28. Okay. So actually for the case where n is 8, there's a better way to create a graph. Yeah. No, wait. Yeah, I think so I think when it comes to 10 vertices, I think according to your method, we can add 20 edges. So I think the formula is just twice the number of edges. So twice the number of vertices. Because first of all, we have all these edges on the cycle, right? And for every vertex, we are going to add 1 2-hop neighbors, 1 edge to its 2-hop neighbors, right? So for every edge, it has 1 additional like diameter edge. So this is why we have twice.
It's not necessarily 1. Maybe
One, yeah, but when it comes to 2, you're going to double count it, right? So if you have this edge, for this one, this is its. This is this vertex 2-hop neighbor. Similarly for this is this vertex 2-hop neighbors. So yeah, so actually we are going to count it twice. So I think your way of creating this triangle-free graph will give us 2 n edges. Unless you add like a 3 hop neighbor or 4 hop neighbor, and then you have more edges. But if you only consider 2 hop neighbors, then I think this is the number of edges you have.
Just take this for example.
Mm-hmm.
So you have one line like this, right? And the other line is going to be vertical. Almost vertical, right?
Like this one.
Yes.
Yeah.
And after that, you have 2 more edges. So you can consider like the
I'll give this versus some labels, okay? 1, 2, 3, 4. Okay.
so you can think of like the first step is draw a circle like contain
Yeah.
those vertices, right? And the second step is going to be like this, the 2 line for 1, 4, and 1, 8.
Right.
And after that, you have 2 more edges. For example, like 1, 8, you have the new edges. So you can have another algorithm like loop this, so you have 1, 6 as the other edge.
So why can you add this 1, 6?
Because it's 3. 1, 8, 8, 7, 7, 6. So it's 3. Right? It follows the rule. Just like 1, 10, 10, 9, 9, 8.
1, 10. No, you have this edge 1, 10 because we have the edges on the whole cycle.
Because we add the new edge from 1 to 8. So we have 1, 8, 8, 7, 7, 6. It's also 3. So we can make a link between 1 and 6.
Between 1, 6?
Yes.
Then I'm not very sure about your rule of adding edges. Because I thought that your idea is to just add all these 2 hop neighbors.
My idea is we take each vertex. In this example, we take 10 vertices.
Mm-hmm.
So there's a for loop for 10.
Right.
And we start from the vertex 1. And we just start adding edges.
Right.
2x maximum. Like greedy. Just greedy.
Well, all right,
Yeah.
okay.
We just keep on adding until it's not edible. And we go
I
to
see.
the second vertex and keep
I
on
see.
adding.
I see. So when we consider this vertex 1, we can also add 1, 6.
Yes. And after we
All right.
add 1, 6, there's probably a new option because 1, 6 is a new edge. So, for example, we can add. No, we cannot add any.
Yeah, for vertex 1, we can at most add 3 edges. And then we consider vertex 2 and so on. Oh, all right, okay. Yeah, I believe that this is a better algorithm in terms of the number of edges you can add. But the difficulty is that we don't know how to analyze the number of edges we're going to have, right? So actually there's a simpler way to build this kind of triangle-free graph with the most number of edges. So is there a different way of constructing the triangle-free graph? There's a very simple way. 有人有想到吗？所以刚刚那个方法比较像是一个 greedy 的做法 ，OK？ 但 greedy 的问题就是比较难去分析，就是它会有几个 edge。So I'm going to give you a hint, okay? So the hint is to divide this the set of n vertices, or in this case, 10 vertices, into 2 sets, okay? Each set has 5 vertices, okay? So here we have 5 vertices, and 5 vertices for this set. Okay. So how to add edges without creating triangle? Okay, so the way we're going to add edges is the following. Okay, so we will not add edges within these two sets. Okay, so all these edges are like connecting these two sets. Okay, so we have 5 and 5 there. So we're going to add as many edges as we can between these two sets. All right. I'm not going to draw all these edges. So the idea is to divide this vertex set into two sets, where each set has like a similar size. So in this case, when the number of vertices is an even number, indeed these two sets can have the same size. And then we're going to add all the edges between these two sets. Okay, so this will give us 25 edges. Okay, and also we're going to show that 25 is the best you can do. Okay, but first, can you see why this graph has no triangle? Can you find a triangle here? Because if there were a triangle here, this will imply that there's some edge that connects some vertices that are within the same set. Okay, that's the only way to create a triangle for this graph. But at the beginning, I stressed that we do not have any edge that connects vertices within the same set. Okay, all these edges are between these two different sets. So this graph certainly is triangle free. Okay. So now the question is, so can we do better? Okay, is there a triangle-free graph that has 10 vertices and more than 25 edges? Okay, so that's the next statement that we're going to prove. Okay. All right, so this is a very famous claim in what we call the extremal graph theory. So in extremal graph theory, we're going to consider problems like this form. So we want to have a certain property, like here, triangle free. And we want to find the maximum possible of some parameter, like in this case, the number of edges. Okay, so you can also consider problems like you want to have like, for example, cycle free or C4, C5 free graph. Okay, you want to have certain property, but then you want to maximize something or minimize something. Perhaps another example is to have a kinetic graph. So if you want to have a kinetic graph, then what is the minimum number of edges you must have? Okay, or if you want to have the property that the graph is disconnected, and what is the most number of edges you can have, right? So problems like this are studied in the branch of extremal graph theory. So I think this is one of these classic results in this branch of graph theory. Right, so yeah, so back to this claim. Do you have any idea to prove this claim? Because the only proof that I know is kind of genius. So I'll be interested to know if there's some straightforward or simple proof. The proof that I'm going to tell you will be simple, right? But not straightforward. So we're going to consider another claim. Okay. Okay, so we're going to consider, once again, this graph, the same graph, but this time we're going to consider its maximum degree. Okay, so let's call delta the maximum degree. Okay. So the claim says, once you have this maximum degree, okay, so suppose the maximum degree is 5, right? Then you can actually upper bound the number of edges, okay? So this upper bound is quite simple. So it's just m minus delta times delta, okay? So once we have this claim, we can automatically prove this, the original claim that we try to prove. Okay, why? Because this product is maximized because we want to have the most edges. So we want to maximize this term. So this term is maximized when delta equals n over 2. So when delta equals n over 2, then this product equals this one. OK？ 所以我刚刚说的事情是，我们不会直接去证上面这个 ，OK？ 上面这个我不知道什么比较直接的方法 ，OK？ 所以我们会去看下面这个。那下面这个他要看的事情是，你只要跟我讲最大 degree 是多少，你手上有一个 triangle free 的 graph， 然后你跟我讲它最大 degree 是多少，我可以马上就会跟你讲说这个 graph 它最多有几个 edge。那这个最多有几个 edge 呢？就是这个 maximum degree 再乘上 n 减 delta。OK， 那为什么说有下面这个你就可以有上面这个？因为这个 n 减掉 delta 再乘上 delta， 假设这个 delta 是一个变数，那这一个乘积它什么时候会是最大？就是当 delta 是1半的时候。OK， 你自己可以去试，譬如说你可以试 n 是10的时候，所以10减掉 delta 乘上 delta 什么时候会是最大？就会是那个 delta 是就是刚好10的1半的时候会是最大的 ，OK， 所以那这样子这个结果就会跟上面是一样的。Alright, so let's call this claim 1 and this claim 2. So by claim 2, a triangle-free graph has at most m minus delta times delta edges. And this is at most, or maximized when when delta equals n over 2. Okay. So this immediately gives us claim 1. Okay. Okay, so this means that we can forget about this claim. Okay, we can focus on this claim 2, where we have this maximum degree delta, and we try to formulate the number of edges with this delta. Okay. So the assumption is still the same, okay? We cannot have a triangle, okay? And we want to see what is the upper bound of number of edges we can have for this triangle-free graph.有任何想法吗？所以我们要做的事情就是想办法找一个 edge 数的上限 ，OK， 然后这个 edge 数的上限会跟最大的 degree 有关。所以换句话说，如果我今天跟你讲这个 graph 最大 degree 是多少，那你可不可以根据这个资讯，然后跟我说这个整个 graph 最多会有几个 edge？ So we have a vertex of degree delta, okay? So this means it has delta vertices as its neighbors. Okay, so let's call this maximum degree vertex V. So V has the most neighbors in this graph. And let's call this set of neighbors n of V. All right, so this is pretty much all the assumption we have. So obviously there are some vertices that are not adjacent to this vertex V, okay? So in other words, we have this set, okay? So this set is just the vertex set minus the neighbors of V, okay? So it's like we divide the whole vertex set into two parts. The first part is the neighbors of V, where V is the maximum degree vertex, and the other set is just the rest of vertices in the graph. So if you look at this product, so what is the physical meaning of m minus delta for this picture? So what is the size of this blue set? M minus delta, okay? Right, because n is just the number of vertices in the whole graph, and delta is just the size of n of V, okay? So the size here is delta. So can you see where we have this product in this graph? Somehow we need to like multiply these two terms. And also this graph has no triangle, okay? So what can you say about this triangle-free graph property? So this graph has no triangle, therefore we cannot have edges within this n of v, okay? Because, for example, if we have an edge that is between two neighbors of v, then we'll get a triangle, okay? So we cannot have edges within n of v. Okay.所以有什么想法吗？基本上我们已经把所有的资讯都放在上面。Okay, one more hint. So if it's no edge within this n of v, this will imply that every edge is instant to some vertex in this blue set. Okay. Now we only need the last step to finish the proof. So this says that if there's no edge within n of v, this means for every edge. So for every edge, we have two endpoints, okay? So this says you cannot have both endpoints within this red set, which implies that at least one of its endpoints is in this blue set. Okay, so every edge in this graph has at least one endpoint in the blue set. Okay, so that's why every edge is instant to this blue set. So哪一个是最大？
那个 n 减掉它是delta是最大的想法。那我没有一个比较好的就是数学描述。
啊哈。
对，就是因为那个 n 就是 n of b 那边不会有 h 相应，那这边的那个 b minus n of b 那边可以跟这边做相应的话，那不就是两边？如果n 减掉它那个集合里面所有的点都它所连到的 delta 都是连到右边那边的话，那基本上它就是最大的情况。因为只要漏一个的话，就会比较小一点，就会 h 数就会少一点。
啊哈。
对，所以
对，很接近，但是会需要再稍微更明确一点。对，很接近，非常接近。
我在想，就是如果这样数学要实证。Is it because that is maximum
okay?
So in the blue set,
Yeah,
if we make each vertex in the blue set the maximum degree delta,
right.
which means in the blue set they are maximum and they are identical to V, vertex V. So there are n minus delta V vertices. So there are n minus delta times delta edges.
No,
Which is
no.
maximum.
Yeah, the number of vertices in this blue set is exactly m minus delta.
Yeah.
Yeah, so you cannot change this because this is just all the vertices in the graph,
No,
excluding
there are
n of v.
minus delta vertices, and each vertices has delta edges, which is maximum. So they are identical to V. They are the same, right? If you know what I'm saying，就是 V 每 n 减 delta 这个蓝色这个里面的每个点，它跟 V 都一样，都有 edge 到那个 n，就是它跟 V 连的 neighbor 都一样。
这个 part 我觉得有点怪怪的，你说会等于 v 这个 part 怪怪的。这个 say 就只有这样子，它不会等于 v。
就是它们里面每个点都跟 V 一样，它连的 neighbor 都跟 V 一样。
跟 v 一样 ，v 就是整个所有的。
只有 V 不是个点吗？
Oh, okay, you mean this v? Okay. Not necessary. Okay. I mean, the number of neighbors or their degrees can be the same, but the set of neighbors can be different. Right. So, for example, this vertex in this blue set, it can have all its neighbors within this blue set. Yeah, but you're right about one point, that is for every vertex in this blue set, the degree can be delta. That's for sure, yeah.
But my proof is like another way to prove this. It's because you assume the maximum degree is delta. So if we can make the blue set vertices, each of the vertices has the degree of delta, which we can prove is the maximum edges because we maximize each vertices degrees. So the way to do this is to that each vertices in the blue set have identical edges to V, the vertex V, which means they are connected to all the edges in the red part, which is the V.
Yeah, I see your point, but yeah, but here the problem is this G is an arbitrary graph, so you cannot just assume that this vertex has all the neighbors in this n of V. So this is just any graph, and the only property or condition we have is it is triangle free. Okay. All right, so let me finish the proof. Okay. So now what we have is that every edge is instant to this blue set, which implies the number of edges in the graph is at most the total degree of the blue set. Do you agree? Okay, so for every edge, now we want to count the number of edges. Okay, so to count the number of edges, now we know that every edge has at least one endpoint in this blue set. So we can just count the degrees, the total degree in this blue set. So yes, there may be some double counting, right? So for example, if we have an edge like this, then we'll count this edge twice when we consider total degree of this blue set. But nonetheless, we just want to have an upper bound, okay? So I want to find some number that is greater than the number of edges, okay? So that we can have an upper bound. So this holds, okay? And then the rest is simple, okay? So what is the total degree of the blue set? So the total degree of this blue set is at most what? Well, we have m minus delta vertices. And since we want to compute the total degree, and we know that for every vertex, the degree is at most delta. So the total degree is at most m minus delta times delta. Okay? So let's look at the proof again, okay? So starting from the assumption that the graph is triangle free, we get that we cannot have an edge within this red set, which are just the neighbors of this maximum degree vertex V, okay? So we cannot have an edge like this, okay? We cannot have this edge, okay? Because it is triangle free, okay? Now, once we know that there's no edge within this red set, we get that every edge has at least one endpoint in this blue set. So we cannot have an edge whose both endpoints are within this red set. So at least one of them must be in this blue set, okay? So after that, we know that since every edge has at least one endpoint in this blue set, and we want to have an upper bound for the number of edges, we can just count the total degree of this blue set. And the total degree of this blue set, well, how do we compute this? We're going to use another assumption that every degree is at most delta. So for every vertex in this blue set, the degree is at most delta. And since there are m minus delta vertices in the graph or in a blue set, the total degree of the blue set will be m minus delta times delta. Okay? So this will finish the proof. Okay. So yeah, I think the proof is definitely not straightforward, but simple. Yeah, and in some sense, yeah, it is, in my opinion, this is quite genius. Okay. So we need to use this maximum degree as the handle of the proof. Okay. So recall that what we want to prove is the maximum degree or the maximum number of edges in a triangle-free graph, okay? So we want to have this result, right? But in terms, to prove this result, we need to get the handle, okay? And the handle here we have is maximum degree, okay? 所以我们这边最后，我们最后就是利用这个 maximum degree 的 vertex 去做出这种 triangle free 的 graph， 它的 edge 一定不会太多个。OK， 好，所以我们先下课10分钟。
对，后面还有其他证明，还是这边证明就这样完了？
就结束了。
所以就变成这个论点，就变成说你要知道一个多少 vertex 它的就是delta triangle free 有多少个 edge 的情况下，你必须要先知道它有最大的多少 degree， 你才可以回去推。
我不会这样说，我会说我们的最终目标其实是最一开始的，就是你只有跟我讲你有几个点，那我想要知道说你给我这么多的点的情况下，我最多可以加几个 edge， 都不会让我产生 triangle， 这是我最终的目标。只是为了要达成这个目标，我们就透过这个 maximum degree 的协助，去说明这个第一个 claim， 对。 All right, okay, so actually one of the reasons that I want to discuss this question is because this graph is called a complete bipartite graph, okay? Okay, so first of all, what is a bipartite graph? So a bipartite graph is just a graph where you can divide the vertex set into two parts, okay? So if for this graph, we have one part on the left and the other one in the right. So after we can divide this vertex set into two sets, we can then add edges. So the property about a bipartite graph is that all these edges are between these two parts, okay? So you cannot have an edge that is within each of these parts, okay? And we're going to consider some problems on bipartite graphs. So let me first give you the definition. Okay, so let's call these two parts x and y, okay? Okay, so visually you have one part x and another part y. And in a bipartite graph, all edges are between these two parts. Okay? And if it is a complete bipartite graph, then for every pair of vertex in x and y, they must be connected by one edge. Okay? And also in our previous discussion, we used the property that if a graph is bipartite, then you cannot have a triangle, okay? Because to have a triangle here, you must add some edge within these two sets, okay? So a very simple property is that a bipartite graph is triangle-free. So actually, we can slightly generalize this result. Okay, so a triangle is like a cycle. Okay, a cycle of three vertices, right, or three edges. So in fact, if we denote by Cn, so Cn is a cycle of n edges. Okay, so delta is C3, okay? And if you have a square, then it's C4. Okay. So can we have a C5, a cycle of 5 edges in a bipolar graph. So this is C5, okay? So is it possible to have a bipolar graph which contains C5 as its subgraph? Okay, let's try, okay? So suppose, because if it is a bipolar graph, then we can divide the sets or divide the vertex set into two sets, X and Y, okay? So suppose this one is in X, right? And because it is a bipolar graph, then we can conclude that these two neighbors of X, they cannot be in X. So therefore, they must be in Y. Okay? And following the same idea, for this neighbor of Y, this one cannot be in Y, okay? Otherwise, we'll have an edge within Y, okay? So this one must be in X. So similarly, this guy, which is a neighbor of some vertex in Y, well, this one must be in X, okay? But then you can see that there's a contradiction, okay? Because here we have an edge within X, okay? So actually, we cannot have C3, we cannot have C5, and I think it's easy to see that we cannot have like C7, C9 in a complete graph. Oh, sorry, in a bipolar graph, okay? So a bipolar graph cannot have odd cycles. Okay? For example, C3, C5, C7, and so on. Okay? Okay, so can we have even cycles in a bipolar graph? So for example, like this one, a square. Is this one a bipolar graph? Visually, it may not look like a bipolar graph where you have two parts, right? X and Y. So, but actually, this one is bipolar. Okay. So the way we divide this vertex set is like this. Okay. So in this partition, okay, we do not have edges in X, and similarly, we do not have edges in Y. So all edges are between X and Y. Okay, so this one is a bipolar graph. Okay, so a bipolar graph can have even cycles, okay, but not odd cycles. Okay. All right, so this is a very simple property about bipolar graphs. So actually, we can consider the other direction, okay? So here we say that if a graph is bipolar, then it cannot have odd cycles. Okay? So what about the other direction? So suppose I know that a certain graph has no odd cycles. So can we guarantee that the graph must be bipolar? Okay. So is this one correct? Okay, so how to show this?
因为你先假设一个起点，然后那个起点在 x，
嗯哼，
所以它下面那个会在 y 嘛，
嗯哼，OK，
然后如果它有极环的话，那就会那它走那个环的步数以后，它就会连到就是跟原本同一个 part。
啊哈，所以你的假设是什么？你的假设是，
假设起点是 x，
所以假设它是bipartite，
对，
还是怎么样？
没有，假设它有极环，
啊哈，假设它，对，可是我们现在要证的是这个，对。有什么想法吗？
因为如果它是 no R cycle，对吧？它只有两种情况，一种是 even cycle 或是 no cycle。
对，
那这两个都会是bipartite，
所以为什么？所以为什么？
even cycle 可以是bipartite，那 no cycle 也可以是bipartite，一边都是有，一边没有。
那我们刚刚前面讨论是，如果你是 bipartite graph，你可以有 even cycle， 但我们并没有说，如果你有 even cycle， 你就会是，对。
我们假设起点的地方是0，然后那个隔壁的是1嘛。
哈哈。
然后如果它没有极环的话，就表示它的只能点到偶数的标记上。奇数的。
啊哈，然后你说，
然后如果它的0有到0的边的话，那它就一定是极环。
啊哈，
所以它这两个之间一定会有边，所以它很快换。
对，所以我这边我想要把逻辑弄清楚，就是所以你的假设是什么，然后你想要说明什么？
可以先随便找一个点，然后假设那个起点是 x， 然后我设它颜色是黑色，然后把跟它相连的颜色都染成白色，然后我再把跟白色相连都染成黑色，然后把黑色放一边，白色放一边，黑色跟白色就是黑色跟黑色绝对不会有边，然后白色跟白色绝对不会有边。
为什么？
因为它没有计划，所以它不会是黑白。因为它没有计划，所以它不会同时是黑色也是白色。
OK， 所以可以再讲一次，你刚刚怎么涂颜色呢？
先挑一个起点，
嗯哼，
然后把它涂成黑色，
嗯哼，
然后把跟它相连的都涂成白色。
跟它相邻的都涂成白色。
对。
然后呢？
把跟白色相连的，就是做 DFS。
啊。
然后把跟它相连的，把它周围再涂黑色。
啊哈。
然后没有被投场过的，再把它涂成黑色。
啊哈。OK， 然后，对，这样子就有一个 coloring 的 scheme， 那然后呢，有了这个 coloring， 所以我猜你的白色就是bipartite的一个 part， 黑色就是另外一个 part， 所以那你要怎么说明说白色的不会有相邻，然后黑色的不会有相邻？
假设它没有环的话，那这个一定是对的，而且它就是很多 path， 然后就走过去。
对。
然后如果它有环，它只会是偶数。
对，对，
所以它颜色就不会冲。
没错，没错，但是这中间有一些细节，我想要再把它弄得更清楚一点。对，就刚刚最后那个步骤是，如果它没有 art cycle， 那这样黑色跟黑色一定不会相邻，白色跟白色一定不会相邻，就这一个逻辑的 transition。
就是它有个环嘛，所以它是黑白黑白黑白黑白，然后起点跟终点会是同，就是它会从地方出发，黑白黑白。所以假设它有基环的话，那它起点跟终点的颜色会从，如果它是偶数的话，黑白黑会刚好会到一个，会刚好是不同的。
嗯哼。没错，我会说基本的 idea 就会是这样子。那我会在第一次作业里面给大家出一个题组，然后这个题组会要让大家去比较 detail 的把这个步骤写出来。OK， 那基本的 idea 就是这样子，只是那中间那个有一些过程就没办法讲得非常清楚。所以我们等一下我们在作业里面会去让大家做这件事情。有点 tedious， 所以我不想在这边讲 ，OK？ 那 anyway 这个结论会是对的 ，OK？ 所以如果这个 graph 它没有 art cycle， 那它就一定会是 bipartite，OK？ 所以这个方向也是正确的 ，OK？ All right, so the reason I want to bring to discuss this bipartite graph is because next we're going to consider a problem on bipartite graph, and the problem is maximum matching. Okay, so let me give you an example, okay? So this is a bipartite graph, okay? And what is a matching? So a matching, it's like to match vertices, okay? So in order to match vertices, you have to make sure that no vertex can be matched to multiple vertices, okay? So it's like a one-to-one mapping. So for example, we can pick this one and this one, okay? So this is a matching, where we match these four vertices, okay? So some vertex is not matched in my solution, okay? And the goal for this problem is to find like the largest matching you can have, okay? By largest, I mean the most number of edges in the matching, okay? So first of all, the definition of matching is just a set of edges that do not share endpoints. Okay, so like these two edges, so they do not touch, okay? So they do not share endpoints. And so if you further add this edge, then this is no longer a matching because these two edges, they share endpoint. Okay? So this is the definition for matching. And for the maximum matching problem, we just want to find the largest matching. In other words, we want to maximize the number of edges. Okay? So similar to the problem we considered for the previous class. We want to maximize the number of edges, okay? But this time we want to have a matching, okay? Okay. So actually, you can also consider this problem on non-bipartite graphs, all right? But the algorithm is much more complicated than bipartite graphs. So for this course, we'll focus on bipartite graphs. And for bipartite graphs and non-bipartite graphs, we can have polynomial time algorithm, okay? So yeah, so if you're interested in non-bipartite graphs, you can just Google maximum matching, general graph, or non-bipartite graphs. Okay. All right, so for this course, let's consider bipartite graphs. So given a bipartite graph, we want to find the maximum matching. So any idea of finding the maximum matching? 给你一个 bipartite graph 要怎样做才可以找到最大的 matching? What path? So what is complementary path?
先假设它是有向图，然后再做 back， 什么问题？就是先找 max， 就你先随便点一个最大的，然后开始找能不能，就你先点一个最大的时候，把所有的 down edge 都，就把所有的，把绿就以那个例子好了，先找最大，所以是绿色，把所有的绿色变成 down edge， 然后呢，其他非绿色都是 upper edge。然后接下来就是要找一个 path， 可以是连成一条。
Okay. Yeah. Anyway, you want to find some path, all
然后
right?
如果有那个 path 的话，就可以拆掉重叠。
Okay. Okay. So I believe the standard way to call this path is augmenting path. Okay.
Augmenting path 不是那个水。我有它的特色。
So I'm trying to say alternating path because another path that we're going to consider is M alternating path, okay? So so let me give you the intuition behind the algorithm, okay? So suppose now you have some matching, not necessarily the largest one, okay? For example, in this simple graph, we know that this green edge alone is not the largest matching, okay? So the algorithm is to find a way to make this matching larger, okay, to enlarge this matching. And to do so, we're going to find a spatial path, okay? So in this path, this spatial path, so in this spatial path, we have two properties. So the first property is that this path is like alternates between edges in the matching that you have and edges not in the matching. So in this case, edge is not a green edge, and not a green edge. Okay, so it is alternating between edges in the matching and edges not in the matching. Okay, so let's call this green edges. So let's call this M. Okay, so we have a matching M and want to find a larger matching. Okay, so the first property is that the path P, like this one, it alternates between edges in M and edges not in M. Okay. So this is the property, the first property. Okay. And the second property is that the two endpoints of this path is not matched by M. Okay. So we have a special way of saying this. So we're going to say that the two endpoints are not saturated by M. So basically, this is just said that the two endpoints are not matched by M. Okay. So once we have this alternating path, augmenting path, okay, we can find a larger matching. Okay, so how to find a larger matching? Okay, we just swap these edges. So for the edges on the path, if it is not in M, then we're going to add this edge. And if it is in M, then we're going to remove it. Okay? So after we find this augmenting path, we can have these two edges, okay? Because these two edges are on this path P, and they are not on this green edge matching M. Okay, so the structure of the algorithm is the following. Okay, so first of all, we find a maximal matching. So in fact, we can find any matching we want. Okay. Okay, so here I said maximal instead of maximum because this is just a local maximum matching, which means a matching where you cannot add any more edges. Okay. So for example, this green edge alone is a maximal matching because after you have this edge in your matching, you cannot add any more edges to the matching. Otherwise, you're going to share the edge endpoints. Okay. So this matching M is local maximum or maximal. Okay, and after we have a matching M, we're going to find a larger matching by finding the M augmenting path. Right? So call this path P. And then we're going to use this path P to find the larger, to find the larger matching. So to do so, we're going to take the exclusive OR. Okay, so what is this exclusive OR? So in this example, okay, we know that we will take this edge and this edge, but not the one in the middle. Okay? So the reason is that we only want edges that only appear either in the path or in the matching, okay? But not both. So if some edge is on P and M, then we're not going to take this, okay? So we're going to take the exclusive OR. All right, so visually, if you have two sets, A and B, then what is the exclusive OR? The exclusive OR will be like you first take the union, and then you exclude their intersection, okay? So that's exclusive OR. So perhaps I can give you another example. Okay. Okay, so this is the input graph, and you have maximal matching. Okay, so this is the matching you have after step 1. Okay, so this is maximal because you cannot have any more edges added to the matching. Okay, and then we have to find a M augmenting path. Okay, perhaps I'll make it longer. Okay, so this is M augmenting path. Okay, so why? First of all, it alternates between edges in the matching and edges not in the matching. Okay, and secondly, the two endpoints of these two this path are not saturated or are not matched by the green matching M. So it satisfies both properties. Therefore, it is an M augmenting path. And once you have this M augmenting path, you can take the exclusive OR to find the larger matching. So when you take the exclusive OR of these two sets, you get so we still have this one because this edge on the left only appears in the green matching, not on the path. So we can still have this one, okay? And then for the edges on the path, we can take all these three vertical edges because they only appear in the path, not in the matching. So we can take all these three vertical edges, okay? And then we can just repeat, okay? Okay. So this is like the basic structure of this maximum matching algorithm, okay? But there are some problems behind this algorithm. So first of all, is it possible that, say, we have a matching M, and this matching M is not maximum? Okay. So the first question is it possible that we cannot have an M augmenting path? Right? Because, say, the maximum matching has 3 edges, and your matching now has only 2 edges. Is it possible that you'll never find an M augmenting path? Because according to your algorithm, if you cannot find an M augmenting path, you cannot find a larger matching. Yeah, but we need a proof. So yeah, so the result or the answer is no. Whenever your matching is not maximum, you always find, or there always exists an M augmenting path. So it kind of tells you that the algorithm is correct, okay? Because whenever your solution is not the best, there's always an M augmenting path waiting for you to be found, okay? So this is like the first question that we're going to consider. to show that whenever your matching is not maximum, we can always have an M augmenting path. And the second question is how to find augmenting path, okay? So this is the second question. So this is like an algorithm design question. And the basic idea is just like what Yo Tongxue says. I recall that your last name is Yo, right? So the idea is to create a tree, okay? Starting from some vertex, and we're going up and going down to find this M augmenting path, okay? And the third question is, what happens if our algorithm cannot find an M augmenting path? Now, this algorithm must end at some point, okay? We cannot have this endless for loop. It must end at some under certain condition. So what is that condition? So when the algorithm stops, is there a way to show that the solution you have must be optimal, must be the best? Okay? So we have 3 questions. So the first one is about existence of augmenting path, okay? So if M is not maximum, is there always an M augmenting path? It better be true. Otherwise, your algorithm may not find an M augmenting path because it does not exist. Okay? But as I mentioned earlier, the answer is true. Okay? So whenever the matching is not best, you can always find a way to improve it. And the second question is how to design an algorithm to find M augmenting path. Okay? So this is an algorithm design question. Okay? And the third question is how to show that the algorithm produces the best solution. So since our algorithm just keeps finding augmenting path, for the third question, it's like when the algorithm cannot find an M augmenting path, is it true that the matching we have is already the best? Okay. So next we're going to answer these 3 questions. Okay. So first of all, we're going to consider the existence problem. Okay. So we have matching, and we know that it is not the maximum matching. So how to show that there always exists an M augmenting path? So suppose you have a matching of size 3, and the best matching has 4 edges, how to create an M augmenting path using these 2 matchings. 我们第一个要想的就是，因为我们刚才演算法就不断的找到 augmenting path， 所以我们要确保是，如果你手上的 matching 不是最好的，那是不是保证一定可以找到 augmenting path， 或证明说一定存在 augmenting path？ 因为如果说有可能没有 augmenting path， 那我们的演算法就会是错的。So you have 2 matchings, and these 2 matchings have different sizes. So M is smaller, and M star is larger. So you can think of this M star as like the maximum matching. Okay? And M is the matching you have so far. And we want to show that if the matching you have is smaller than the best matching, then there's always an M augmenting path. Okay? So it's like you have to create or construct an M augmenting path using these 2 matchings, because these 2 matchings are the only edges we know, okay? And we want to use these edges to create an M augmenting path. So 有谁看得出来我要怎么利用这2个 matching 去建一个 M augmenting path 吗？所以 M augmenting path 再重复一次，就是它会 edge 会交替出现 ，OK？ 然后第二个就是这个 edge 的2个端点，因为我们就是要让它变得更大，所以这2个 edge 的端点它就不能被 M match，OK？ 所以这2个端点一定是没有在 M 里面的，对，视觉上有点像这样子。如果是这样的话，那它就不是一个 augmenting path， 因为假设绿色就是 M，OK？ 它是一个 alternating path， 因为它会交替出现，但是呢，它的这2个 endpoint 并没有说都没有被 saturate，OK？ 都没有被 match， 所以这个就不是 augmenting path。然后我们想要的是像这样子。然后这2个并没有被 match， 并没有被这个绿色的 edge match。OK， 我们想要做找这样的 path 出来，所以要怎么样找才可以找到这样的 augmenting path？ All right, so because M and M star are the only edges we can use, so we can only just focus on edges in M and edges in M star. Okay, so just consider edges in M and M star. Okay. So this is one example. Okay. So the green edges are edges in M, and the yellow edges are edges in M star. Okay, so both matchings can perhaps they can share edges, like this one. Okay, so this one is in M and M star. Okay, and they can also form a cycle. Okay, and like an alternating cycle. Okay, that is also possible. So we want to find an M augmenting path by just looking at their union. All right, so first of all, we can ignore edges like this, edges that are shared by both matchings, okay? So to do so, we can just take the exclusive OR, because by taking the exclusive OR, we can get rid of these edges that are shared by both endpoints, by both matchings, okay? So we can just get rid of these shared edges. And let's consider the components, okay? Okay, so for example, here we have two components. Okay. So let's try to find some properties about these components of M exclusive or M star. Okay. So first of all, what is the degree? If we only consider the exclusive of these two matchings, what is the maximum degree of a vertex? 我们这边只看这两个 matching， 就是你手上有的这个比较小，跟实际上比较大的那个 matching。我们看这两个的 exclusive OR， 我们的目标就是要想办法从里面找到一个 augmenting path， 去证明说 augmenting path 一定存在。那我们现在要做的事情，就是要想办法找到这些 component 的一些性质，去说明说，里面会有augmenting path。所以我刚刚问的问题是，这每一个点的 degree 最多是多少？ So at least from this example, the degree is at most 2. So why? So why the degree is at most 2? Exactly, because we consider edges in the matching, and we have 2 matchings. So every vertex is like instant to or adjacent to at most 2 edges. Okay. So if degree is at most 2, then what does the component look like? So if every vertex has at most 2 neighbors, then the component must be so you either have degree 1 or degree 2. Okay? You cannot have degree 0 because only consider edges in the matching. So as from this graph, you can see that every one has at least 1 neighbor because we only consider edges in M and M star. So every vertex is instant to or adjacent to at least 1 edge. So you can have at least 1 neighbor. Okay. So 1 over 2.所以如果这 component 里面每一个点都只有2个或1个邻居，那这 component 会是怎么样？如果你看这边的 component 的话，基本上就只有2个可能，就要么它就是一个 path， OK， 所以像这个 ，OK， 所以一个 path 就是这2个只有它的2个端点是 degree 1，中间都是 degree 2， OK， 或者它是 cycle， 如果是 cycle 的话，就每个点的 degree 都刚好都会是2，所以就只有这2个可能性。所以如果你已经确定你的 degree 要么是1，要么是2，那你这个 component 一定就会是 path 或者是 cycle，OK， 你不可能会像是有这样子的 ，OK， 这样 degree 就会太大。OK， 好，我们先下课，所以等一下会说明，就是这个其中一个 path 一定就会是 augmenting path。OK， 好，所以我们先下课。对对对对。 All right, so let's continue our proof. So recall that we want to find an M augmenting path, okay? And we consider the components of the exclusive of these two matches, M and M star. And our goal is to show that at least one of these components must be an M augmenting path, okay? All right, so far we already know that these components must be either a cycle or a path, okay? And if it is a cycle, then I think it's easy to see that it must be an alternating cycle, right? This means that if we consider the edges on a cycle, then it alternates between edges in M and edges in M star. Okay? And if this is an alternating cycle, then the number of yellow edges and the number of green edges on the cycle must be the same, okay? In other words, these two matchings, they contribute the same number of edges in the cycle, okay? Okay. So that's when the component is a cycle, okay? And the other case is when the component is a path, okay? So again, this must be an alternating path, right? So if you consider the edges on the path, then you cannot have two edges that are connected and from the same matching, because otherwise you have two edges in the same matching that share endpoints, okay? So that's not a matching. So we know that, again, this must be an alternating path. All right? And moreover, because we know that M star is larger than M, so at least one of these components, in one of these components, you must see that we have more edges from M star than the number of edges in M, okay? So like this one, okay? So here you can see that yellow edges, there are two yellow edges, but just one green edge, okay? So because M star is larger than M, there's a component where M star contributes more edges. Than M, okay? And this component must be a path, okay? Because we know that if it is a cycle, then both matchings, they have the same number of edges in the component. So the component must be an alternating cycle. Let's call this component C. So C must be an alternating path. Right? Because we show that if it is a path, then it must be alternating. Okay? Okay? And so in this alternating path, we have more edges in M star. Therefore, this must be an M augmenting path. Okay. All right, so let's review the first question. Okay, so in the first question, we want to show that there's always an M augmenting path whenever your matching is not the best. So the way we show this is by taking the exclusive OR of the matching you have and the best matching. Okay, and we can show that it is one component which is an alternating path. Moreover, this alternating path has more edges from M star than M. So this alternating path must be an M augmenting path. Okay. 好，所以这就是我们刚刚第一个问题的部分。OK， 所以我们现在知道说，如果你手上的 matching 不是最大的，那铁定有一个augmenting path 等着被你找出来这样子。OK。当然你不可以用我们上面这个 proof 的方法，因为如果你 follow 这个 proof 的方法，你要先有那个最好的 matching， 然后去看这些 component， 那很明显你没有那个最好的 matching， 所以这个 proof 并不是演算法，这个 proof 只是说服大家说，当你的 matching 不是最好的时候，你可以很放心，一定会有一个 augmenting path， 你可以拿来用，然后让你的 matching 变得更大。OK， 所以这只是为了要去证明说。augmenting path 一定是存在的，如果你的 matching 不是最好的。Okay. All right. So moving on to the second question. Okay. So now. We want to find an M augmenting path, and we want to have an algorithm. All right. Okay, so let me give you an example. Okay, so this green matching is the matching you have, and you want to find an M augmenting path. Okay. So the first step is to find like a starting point. Okay, because in a path you have two endpoints, so we're going to find first the first endpoint. Okay, and we know that if it is an M augmenting path, then the two endpoints must be not saturated or not matched by the green matching. So we'll just focus on this guy. Okay, so we're going to start here. Okay, so in general, the first step is to find all the unsaturated vertices from some part, like say. This is X and this is Y. Okay. So the first step to find an M augmenting path is to identify all the unsaturated vertices from X. Okay. So let's call this set U. Okay. So U stands for unsaturated. Okay. Okay. And then we'll just to extend M alternating path, okay, from U. Okay. So we're going to proceed in rounds. Okay. So in every round, we're first going down and then going up. Okay. So this is what we do in every round. Okay, so and because we want to find alternating path, okay, so we're going to maintain two sets, and these two sets are quite important because for question 3, where we want to show that the solution we have is the best, we're going to use these definitions. So we're going to maintain two sets, S and T. So what is S? So S is just the set of vertices in X which can be visited by M alternating path from U, okay? OK， 所以这个 S 就是说你从 U 出发，那在这边在这个例子里面 U 就只有这个点而已 ，OK， 所以 U 就是那些没有被 saturated 的点，因为我们要找 augmenting path， 所以它两个端点一定都是没有被 saturated。所以从这些点出发然后你就走 alternating path，OK， 然后如果这个 alternating path 它经过的是在 X， 那它就会被归到 S。那如果这 alternating path 它经过的是在 Y， 那就会被归类到 T。所以这下面的定义跟上面是很像。OK。So in the beginning, S contains just U, okay? Okay, so these two steps are like for initialize this algorithm, okay? So we have two sets U and S, okay? So in every round, we're going to like expand these two sets S and T by extending alternating path, okay? And to create alternating path, starting from, for example, this vertex here, we're first going down. And when we're going down, we must use some edges that are not in the matching, all right? So edges not green, okay? So first we're going down, and then we're going up. And when we're going up, we must use edges from the matching because it is an alternating path, okay? So this is just a round. So for every round, we just pick a vertex from S, okay? Because we want to expand S and T. So we're going to pick a vertex from S, and then going down and going up, okay? So when we're going down, we only consider edges not in the matching. And when we're going up, we only consider edges in the matching. Okay? 所以在每一个回合里面，基本上我们就会去延伸 alternating path。Okay. I think I should put it in the next slide. All right, for example, suppose we take this one, and then we're going to consider edges not in the matching. Okay. And let's call this vertex V, okay? So V is the one that we choose. Okay. So then we'll consider the going down edges. So this means we do not consider edges in M. Okay, so we're going to consider edges that are not in the matching and adjacent to the vertex V that we choose. So we consider edges in this form. Okay. So we're going downward and add this vertex to T. Okay, and then we're going up. Okay, so actually here we have two possible cases. The first case is that this vertex that we just found is not saturated. So in this case, we just found an M augmenting path because we extend this alternating path and we reach some vertex in Y that is not saturated. So if it happens to be the case that the vertex we reach is not saturated, then there's an augmenting path. Otherwise, if it is saturated, this means we have an edge that is in the matching. So we can go up. Okay? So there are two cases. Okay, so the first case is when U is not saturated, sorry. Okay, or unsaturated. Okay, so if U is not saturated, then there's an M augmenting path. Okay. And if U is saturated, then there must be an edge in the matching. Call this edge UW. Okay. Okay. So in this example, this will be W. And we just add this W to the set S. Okay, and then we just repeat. Okay, repeat until we cannot pick a vertex in S. In other words, we have checked all the vertices in S. Okay, so in that case, we're going to finish the algorithm. Okay. Okay, so let's apply this algorithm to the previous example. Okay. Okay, so let's see round 1. Okay, so in round 1, this vertex, because it is not saturated by the green matching M, so it is in U. So initially, the set S only contains U. So this this vertex is also in S. Okay. All right, so we only have one vertex in S, so we can only choose this vertex as V. Okay. So this corresponds to the vertex V we choose in the first step. Okay. And then we're going to consider edges not in the matching. Okay. So we're going to consider this one. Okay. So this one will be U. So we're going to check, okay, see whether this vertex is saturated or not, okay. So in this case, it is saturated by M. So we're going to consider the edges, the edge in the matching that is adjacent to this vertex U. So this guy, okay. So we're going to add the M point W to the set S. Okay. Okay, and this finishes the first round. Okay. Now let's consider the second round. Okay. Okay, so again, the first step is to always choose a vertex from S, okay? So this time we're going to consider this one, this vertex, okay? The vertex W that we just choose in the first round. So this time we're going to choose this vertex, so we call this V, and then we're going down, okay? By going down, we're going to check all the edges not in the matching, which is adjacent to this vertex V. So we're going to consider these two black edges, okay? So this time we have two edges that go down to the set Y. Okay. All right, so for each of these two vertices, we're going to check whether it is saturated or not. So for both vertices, they are saturated by the matching M. So this means we can find a matching, find an edge in a matching that can bring us to X that goes up. Okay. So we have this W, and also we have to add these two vertices U to the set T. Okay. And these two vertices W to the set S. And this finished the second round. So in round 3, we can choose this vertex, okay? So this vertex is in S, and we haven't checked this vertex before. So we can consider this vertex. And then we want to go down to the set Y. But for this vertex, all the edges that are adjacent to V are edges from the matching. So for this case, there's no way of going down to Y. So this just finishes this round, okay? So in this round, we do not add any more vertices to S and T, okay? All right, so next, round 4. All right, so in round 4, this is the last vertex from S. Okay, so first go down to vertex to set Y. Okay, so here we have two candidates. The first candidate U, we have actually considered this vertex before, so we can just ignore this vertex. Okay, okay, because it is already in the set T. Okay, and the other candidate U, again, we have to check whether it is saturated or not. So in this case, it is not saturated. So this means we have found an M augmenting path. Okay. Now, to really output the augmenting path, you can backtrack the algorithm to see how you get or how you reach vertex U. So in this case, the reason we can reach U is because we use this edge. Okay, and since this is an augmenting path, the next edge must be from the matching M. And then we can ask ourselves, how do we reach this vertex here? Okay, so the reason is that we use this edge. Okay, so actually for the algorithm really to output an M augmenting path, we have to memorize some states. By states, I mean how do we reach certain vertex in S and T. Okay, so in particular for every vertex in Y, you can have a variable like a parent, okay? So for every vertex, we have a parent that stores like the previous neighbor or the previous vertex that lead us to the vertex. Okay. So if you want to do this in a pseudocode, then it is in this step. Okay. So, yeah, you can use this information to backtrack the progress of the algorithm to output the final augmenting path. Okay. But anyway, I think the main idea is just to keep extending this alternating tree, all right, until you reach a vertex that is not saturated by the matching M. Okay? At that point, you have found an M augmenting path. Okay. 所以就基本上蛮简单的。我觉得这边的重点就是这两个 set S 跟 T， 因为我们之后会再继续用到这两个 set S 跟 T。所以 S 跟 T 再次强调，就是 S 就是那些你可以抵达的点。那哪一些点呢？就是你从 U 出发 ，U 就是那些没有被 saturate， 就是潜在的 augmenting path 的其中一个 endpoint。我们会从这些 U 出发，然后去长 alternating path 出去，然后看一直长，哎，能不能长到一个unsaturated vertex。在 Y 里面，就在另外一个 part。我们先从 X 出发，然后看最后能不能抵达 Y。OK， 而且这个 Y 这个点是没有被 saturate。那这些过程中经过了这些点，如果它在 如果它在 X 里面，那我们就会说它是在这个 set S。如果它在这个 set Y 里面的话，我们就会说它们就是在 T 里面。OK，right。And also, I think it is easy to see that if I remove this rightmost vertex, okay, if I remove this one, then when the algorithm finishes, it cannot output any augmenting path. Okay, so it depends on the graph and the matching. So in some case, the algorithm just return that I cannot find any augmenting path. Okay, so let's the answer to the second question. Okay, 所以我们刚刚就讲了一个 演算法 ，OK， 这个演算法就可以帮你找到 augmenting path， 如果它存在的话 ，OK， 所以有时候这个演算法也没办法找到 augmenting path。All right, so that brings us to the final question. So the final question is, so what happens if the algorithm cannot output any augmenting path? 对，如果这演算法它没有办法告诉你任何一个 augmenting path， 那你要怎么说明说，真的找不到，或这个你手上的 matching 就是最大的？搞不好是你的演算法不好。搞不好事实上是找得到了，只是你的演算法太烂了，找不到。OK， 所以我们要避免这种状况发生。So I think this is the third question is the most important one. Okay. So in some sense, we want to show that the algorithm is optimal, okay, in the sense that it produces the best matching. So to do this, we're going to provide a certificate, to provide a proof to show that the matching we have is the best, okay? And we're going to consider the following problem. Okay. So next we're going to consider a totally different problem. Okay. So perhaps you're going to feel that why do you even bring this problem? Okay. So the vertex curve problem is the following. Okay. Again, the input is a graph, okay? And in this vertex cover problem, instead of finding edges, because in the problem of maximum matching, we want to find edges, okay? We want to have the most edges, okay? Without sharing any endpoints. But for vertex cover problem, we want to find vertex, okay? And we want to find vertices that can cover all the edges, okay? Okay, so what do I mean by covering all the edges? So suppose, let's consider this vertex, okay? So I said this vertex can cover these three edges, just the edges incident to the vertex, okay? Okay, so in other words, if you want to cover an edge, UV, then you can pick either U or V. Okay. And the problem is really just to cover all these edges. For every edge, you have to pick one endpoint, okay, so that you can cover the edge. And the problem is to find the smallest number of vertices to cover all the edges. Okay. So it's easy to find the maximum vertex cover because you can just pick all the vertices And when you pick all the vertices, then immediately you cover all the edges. So that's easy. So for this problem, this is a minimization problem, okay? So for maximum matching, we want to maximize the number of edges. So for maximum matching problem, it is a maximization problem. But for this one, it is a minimization problem. So we want to find the smallest set of edges, the smallest set of vertices that can cover all the edges. Okay. Yeah. So I think I'm going to change this to the smallest set. Okay. Okay. So for example, in this graph, we can pick these two vertices, okay? So these two vertices are enough to cover all the edges, okay? You can see that this green vertex, it covers these three, and the remaining two edges are covered by the remaining green vertex. So these two vertices can cover all the edges. All right, so why do you want to consider this vertex cover problem? Do you see the connection between vertex cover and matching? So 这个 vertex cover 跟 matching 有什么关系？为什么我们在这边要提到它？哪两个会相等？Yeah, okay. So, OK， 我先 repeat 一下刚才同学说的。刚才同学说的是在 bipolar graph 上面，如果你去看最小的 vertex cover，OK， 跟最大的 matching， 那它们两个会一样大。但这个没有那么明显 ，OK， 所以我想你应该没办法很简单用一句话就可以讲出来，说为什么。
因为你所有的匹配都至少要一个点去覆盖。
对。
所以呢，我们可以知道说，最小点覆盖一定会大于等于最大匹配。
对。
然后那反过来呢，就是如果最小点覆盖如果大于最大匹配的话，那就表示有一个点应该会在就是没有匹配到边的那个点上。
嗯哼。
然后那个点如果它连出去的边如果是连到有匹配的点的话，如果是连到有匹配的那个有被覆盖的点的话，那表示这个点可以移掉。如果旁边那条边是没有被覆盖到的话，那就表示说这个点是必须的。所以呢，就表示说这边可以再加一个新的匹配。
这铁定不会是证明，为什么？因为你从头到尾没有提到 bipolar graph。如果不是 bipolar graph 的话，它们两个有可能是不一样的。对，所以就刚刚那个铁定有一些 miss。对，因为你刚刚的 argument 并没有用到 bipolar graph 的性质。对，所以其中一个方向是很简单的，我们也只需要那个方向而已。所以接下来我要讲的是比较简单，比较大家可以容易看得出来，就是不管你在任何一个 graph 上面。随便一个，也不一定要看什么最小的 vertex cover 或最大的 matching， 不用，就随便看一个 vertex cover， 跟随便看一个 matching，OK？、So this is why I want to discuss vertex cover. because there's a very interesting relationship between these two problems. So say, obviously we want to consider the same graph, okay? So in the same graph, first we find any matching, okay? It can be the best or it can be just some maximal matching. I don't care, just some matching and call it M, okay? And then we find, again, any vertex cover, okay? Not necessarily the minimum one, okay? It can be any vertex cover. Let's call it C, okay? So the ratio between these two sets is that the size of this vertex cover must be at least the size of the matching, okay? So why is that, okay? So why the size of the vertex cover must be greater than or equal to the size of the matching?所以为什么？
不然那条边就没有被看到。
这逻辑有点怪怪的。这逻辑有点怪怪的，是因为有没有可能你用一个点就 cover 很多个 matching 的边？
因为 matching 不会那个。
对，所以刚刚 argument 就没有用到 matching 的性质。对，所以这个会成立一定是这边要是 matching， 所以如果这不是 matching， 这就不会成立。OK， 所以因为这些 matching 它的边都不会有共用边 ，OK， 都不会有共用 endpoint。所以如果假设你有3个 edge 在你的 matching 里面，这3个 edge 它一定都不会共用 endpoint。所以如果你光要 cover 这3个 matching 里面的 edge， 你就至少需要3个 vertex。OK。Okay, so for example, like this matching. Okay, so for this matching, it has 2 edges, and these 2 edges they do not share endpoints. So to cover these edges, you cannot use one vertex to cover multiple edges. Every time you have one vertex, it covers at most one edge in the matching. So say you have 2 edges in the matching, then you have to use at least 2 vertices to cover the edges in the matching, okay? Right, so yeah, so this shows that the size of the vertex cover is an upper bound for the size of the matching, okay? But in some case, this inequality can be equality, okay? So we can change this to equal sign for some graph, okay? So it turns out that if this is a bipartite graph, then, and also you consider the maximum matching and the minimum vertex cover, then these 2 sets have the same size, okay? So actually, after we prove or answer the third question, okay? So after we have the answer for the third question, we can actually prove this claim, okay? First of all, because we only have 2 minutes left, okay? So let's first consider what happens if it is not a bipartite graph, okay? Okay. So according to our previous discussion, if a graph is not bipartite, then it must have some odd cycle, okay? Like this cycle of 5 edges, okay? So let's try to find the maximum matching and minimum vertex cover. So what is the maximum matching? So I think it's easy to see that you can have at most 2 edges as the matching for this C5, okay? So the size of M star is 2, okay? And what is the minimum vertex cover? What is the least number of vertices you need to cover all the vertices? Oh, sorry, to cover all the edges. You need at least 3. Why? Because here we have 5 edges, and every vertex has degree 2. So if you only have 2 vertices, you can cover at most 4, okay? So you have to use at least 3, okay? And in fact, you can choose this, for example, this one, and this one, okay? So in this case, these 2 sets, they do not have the same size, okay? But still, the size of the vertex cover is an upper bound for the size of the matching, okay? So the inequality always holds. But for bipartite graph, the equality holds, okay? So that's it, okay? So next week, we're going to study the third question and prove this claim, okay? So see you next week.